Um, cool. Awesome. Well, thanks everybody. It's really fun to be here and hearing about all the different projects on different parts of the ice field. I'm here today to represent a group of folks from me. I'm at Appalachian State University in Western North Carolina, but also folks at University of Oregon and University of Colorado, where we're focusing on Gilkey Glacier. This is the other side of Camp 18 from what folks are uh, familiar with. This is the down glacier side of Gilkey Glacier, and we're working on a multidisciplinary project spanning these three institutions, sort of looking at both the glacier lake as well as the upstream ice, to try to think about the role of iceberg calving and subaqueous melt in lake terminating glacier change. Um, Oops, I tried to get on a laser pointer and I think I got the wrong thing. I'll just try to not click or I'll highlight random parts of the page. Um, Yeah, so just for motivation, ice marginal lakes are increasing in size and prevalence around the world. I'll illustrate this with Alaska, where we see data here on the left showing the number of ice marginal lakes, meaning like proglacial lakes or ice dammed lakes, basically, in number on the left and then an area on the right. And the key thing for motivating our work is the basically the pink one, which is showing moraine dammed lakes, as well as it's really the pink one is proglacial lakes. These are lakes found downstream from the glacier, um, are growing in both number and significantly in area over the Landsat record. So we see big increases in the size and prevalence of these things. This is work from Bree Rick, who I think has actually been faculty on JERP at some point, potentially. You can read more about in that QR code. And this is important because the formation of a proglacial lake fundamentally disrupts the whole system around it, basically. I'll illustrate this with Mead Glacier in the sort of western side of the Juneau ice field. This is showing the start of the Landsat era in 1984. Going into 2021, we see this large proglacial lake that's over 4 kilometers now has formed that wasn't there in just 40 years ago. And this is really important for a variety of reasons. It is going to allow frontal ablation and melt on the upstream glacier, as well as disrupt the downstream river dynamics and aquatic habitat. And so I've been really interested in these systems in these sort of three different dimensions, both thinking about how is the lake changing, how does it impact the upstream glacier as well as the downstream river system. And so just to motivate that a little bit, essentially the formation of a proglacial lake can really significantly impact the downstream river and its aquatic habitat. And I'll illustrate that with this plot shown here from a paper focused on just mountain lakes in general. But they were going between the upstream side of a lake and the downstream side of a lake and showed that those lakes were associated with increased dissolved organic carbon as well as benthic algae, so sort of like base of the food chain sort of things in the downstream river. Um, we also see significant impacts on the sediment load in the downstream river. This is a plot showing percent glacierized by basin and suspended sediment yield on the y-axis. Um, and you can importantly see, I guess, comparing these red to blue dots here, these are showing maritime glacier-fed river systems that did not have an upstream lake versus ones that do have an upstream lake. And you can see for the same percent glacierized in the watershed, you get much less suspended sediment where you have these proglacial lakes that are then going to impact downstream water quality and therefore creatures that care about that, like salmon and other fish. We've done some work, students working with me. This is Lily Vowell's work, who was an undergrad at App State, who used Landsat data to look at how suspended sediment has changed over time as proglacial lakes in Alaska have formed and grown. And she did this basically relating Landsat reflectance to a relationship between reflectance and suspended sediment concentrations to look at, make these three pie charts here showing river sites downstream from glacier or downstream from glaciers and how suspended sediment is changing, whether there is no lake in that system, whether there's a lake that's been there the whole time, or whether there's new lakes. And we see for sites where there are lakes, the dominant trend we're seeing is declining trends in suspended sediment concentration, as you'd expect with that lake acting like a sediment trap. But interestingly, we've seen that the rate of lake area change, so lakes that are growing really rapidly, aren't necessarily good predictors of places where we see the strongest suspended sediment trends. So it seems like maybe they're more complicated than we expected when we set out to do this study. So there's just sort of like other things that are, I think, make these proglacial lakes so interesting. But the thing that we're focused on mostly in this project that we're working on now is the role of frontal ablation, which is just the sum of iceberg calving, like mechanical calving on the left, and subaqueous melt on the right. And the formation of these proglacial lakes basically turns on an extra mass loss mechanism, where instead of just surface melt, you can now have frontal ablation as well that's eating away at these glaciers. This process has been studied really intensively in marine terminating glacier systems. That's what's illustrated on the left here, where there's a glacier that ends in the ocean, where you have density differences between the outgoing subglacial freshwater and the ambient salt water in the fjord. There's temperature differences in there as well, where the ocean water tends to be much warmer than lake water in these proglacial lake systems. And so it's not exactly clear how much we can extrapolate from marine terminating glaciers into a lake terminating glacier setting in terms of thinking about the mechanics of frontal ablation or how much mass loss might be attributable to that mechanism. However, there is evidence that lake glaciers that end in lakes both flow faster. That's what this left plot is showing. This is glacier speed, where you can see that the lake glaciers are flowing faster than the no lake glaciers. So it seems like maybe there's some dynamical instability associated with these lakes being there. And they've also been shown to lose mass at faster rates, is what the right plot is showing here, where you can see these are both Himalayan examples, but you can see that the glacier thinning rate is increasing over time for both sites with and without proglacial lakes, but the ones that do have proglacial lakes are sort of having accelerating mass loss more rapidly. In my group, we've done some work actually trying to quantitatively assess the amount of mass loss associated with frontal ablation on lake terminating glaciers in Alaska. That's what's shown with the blue dots here, where we show a relationship between glacier area and the mass loss through frontal ablation. And we were able to assess that there's about 0.05 gigatons per year of mass being lost through iceberg calving and subaqueous melt on lake terminating glaciers in Alaska, which is an order of magnitude smaller than what we see for Patagonia. So you can see that big shift in the fit lines here. The orange dots are Patagonian lake terminating glaciers. And so we see substantially more mass loss there. And so that's hinting at this not being a universal process necessarily, that it works differently in different areas. Cool. And so this fact basically that that there's an extra mass loss mechanism in lake terminating glaciers has led people to look at data like are shown on this plot right here, where this is showing the thinning rates for land, lake, and marine terminating glaciers in Alaska. This is using the Huguenot thinning data. But we see that those glaciers that end in water have substantially faster thinning rates than the glaciers that end on land. And so people have kind of attributed this to like, hey, this is the effect of frontal ablation. We're getting this big increase in mass loss. And so we should be really worried about these lakes. But when you look at other factors that vary between these different terminus types, you can see that land terminating glaciers terminate at higher elevation on average, and they're also much steeper on average. And so there are these other things that co-vary with terminus type that make it hard to say like, this is the effect of frontal ablation on these glacier thinning rates versus maybe there's just other things at play, like these covariants with the glaciers being at different elevations or things like that. And so this sort of covariance, I think, motivated our team's sort of approach where we need to have a process-based study that's going to allow us to look at causality in what is the effect of this proglacial lake rather than a correlational study where there's other things that throw a wrench into the assessment of what is the role of frontal ablation on glacier mass loss. And so to do that, we're going to Juneau Ice Field. That's why I'm at this workshop. So folks probably are familiar with this map on the right here, but our study glaciers are these, it's actually probably going to be these two western outlet glaciers, Field Glacier in the little box with a D here. Sorry, that is Gilkey Glacier, the box with a D, and Field Glacier, the box with a C here. Um, and yeah, this is borrowed from the AGU talk. So some of this is known to you guys, but maybe it's helpful to see me pitching why the Juneau Ice Field is so valuable to our project is partly all these little orange squares here and red X's of the stake network, the snow pits, as well as the automated weather stations on the Juneau ice field are really helpful at constraining what is the surface mass balance change that then kind of takes out a variable when we're trying to think about influences on mass change. We don't have that as an unknown parameter as much, thanks to the work by the Juneau ice field research program. And so we can then focus on just what's going on. Yeah, and here's the sites we're focusing on. And basically what we're trying to get at is because there's such good historical data on the Juneau ice field as well as surface mass balance constraint, we can kind of think about the question of are these lakes that we see growing around the Juneau ice field and around tons of other glaciers around the world, are these lakes growing in sort of a passive mode where basically the glacier is being forced by surface mass balance? It's like an atmospheric warming signal. And as the glacier retreats, you just get a lake forming there because there's a low spot there. Or are the lakes playing a more active role where they're actually driving the accelerated glacial retreat? And so our team is trying to basically constrain this problem from different directions, like on the glacier side of the terminus, as well as on the lake side of the terminus, and different timescales as well. So we're using historical data, which is largely from satellite remote sensing. We're out there in the field for a couple years now collecting detailed site observations, and then we're going to model to try to constrain future behavior as well. And we have sort of discipline expertise in glaciology. That's like my part of the project. Oceanography / like I guess it's hydrography because it's not actually the ocean, but that's Dave Sutherland and Victoria Benson at University of Oregon. And then sediment dynamics and like Earth system modeling is Irina Overeem and Jocelyn Reel at the University of Colorado. But so what we're looking at are data like you see here. This is illustrated with Gilkey Glacier that we got out to in summer 2025. It's fun seeing all the different 2025 field seasons for different folks in this room. But this is showing Gilkey Glacier in 1948. This is data from Beth and Davies. By 1979, a lake has formed at Gilkey Glacier. So this has been there for a while now. But in 2022, the lake has grown substantially. It's now over 5 kilometers long, I believe. And yeah, so we have digitized basically every available satellite image to get a detailed record of past retreat of Gilkey Glacier that we'll try to use for thinking about historical variations in frontal ablation. And that is one project that a student, Kaya Wing, working with me has done, where she's basically trying to untangle this retreat time series that you can see on the right here. And the big thing we're taking away from this, I mean, I guess one, you can see the glaciers retreated over 5 kilometers over this 70-year period, but that the retreat is really kind of non-monotonic, I guess. Like you have these sort of periods of quasi-stability or even advance punctuated by a rapid retreat, which we think is due to basically flipping off and on of flotation of the glacier terminus being a really important thing for driving these rapid retreat events at Gilkey Glacier. I've had another student, Carly Kamerdiner, I always say her name wrong, who has been trying to model what we see here. And so she's been using ISSM to try to simulate the retreat of Gilkey Glacier to help us be able to disentangle essentially what is the mass loss from frontal ablation versus what is the surface mass balance driven retreat that we're seeing. And so you can see that illustrated here where the dashed lines are showing model results and the thinner lines are showing that observed terminus retreat time series that we've seen. And so it seems like her model is working pretty well at capturing the sort of time scale of retreat and the magnitude of retreat. Um, and what her work has shown so far, she's finishing her thesis this semester, is that it seems like the retreat time series is really sensitive to like the calving parameterization and pretty insensitive to the surface mass balance. And so you can see here, the black line is our observed retreat, and these blue lines are simulated retreat with different calving thresholds, and it's a von Mises calving rule, and it's just toggling basically how low does the stress need to be to trigger calving once the glacier goes floating. And you can see we're getting big differences in the timing of retreat depending on what that calving parameter is. So it seems like the retreat is really being driven by calving, and importantly, like calving of the floating tongue as opposed to the grounded ice here. And so that is work that's basically been in like the historical or the modeling space. But I want to transition now to field work that we started to do in last summer of 2025. So showing Gilkey Glacier and its lake again here. And I'll basically walk through a few data sets that we've collected here. But the important thing, I guess, is that we're collecting data at the glacier outlet, so we can say what's leaving the lake. We're collecting data on the ice, and so we can say what's going into the lake, how thick is the ice, how fast is it flowing, and then we have measurements in the lake as well, so we know how deep it is, what the temperature is, and things like that. So we're really trying to constrain all different sides of the system to be able to say how much mass loss is attributable to calving and subic base melt. Yeah, and so I'll just walk through some of these data sets we've collected. One of them is multi-beam sonar. So that's illustrated with these figures here, where you can see the little red zodiac we were cruising around on the lake in July. Then we came back in September as well. And this is the terminus of Gilkey Glacier. We ran through the whole lake using a multi-beam sonar system, like you see here. And those produced data that look like this, where we can see that the lake is pretty deep. So we see a maximum depth of about 200 meters that's in this basin right here, where this is the Battle and Thiel glaciers coming in from the south. But right at the tributary junction between Gilkey and those glaciers is where we see the deepest lake depths of around 210 meters. And at the terminus, we have a pretty deep water as well. So we're something like 150 meters water depth at the terminus. One thing that kind of surprised us, and maybe shouldn't have, was that the lake is really flat. I at least naively expected to see like a U-shaped valley, and I guess we sort of do here. But it seems to me to have significant post-glacial sedimentation in the lake basin, and so I'm showing you a topographic profile along this yellow line here, going from the glacier left margin to glacier right, or sort of bottom to top of that map image. And I fit the bathymetric data, the blue data here, to try to get a guess of where the original bedrock surface might be, is what the orange line is here. And it seems like there's been significant sedimentation. Something like 42 meters of sedimentation is what this simple estimate would suggest. And as we move across the lake, our estimates are that we're getting a median sedimentation of something like 30 meters of post-glacial fill. And again, the glacier has only left this spot in like the last 40 years, so pretty rapid sedimentation through the lake. The multi-beam sonar allow us to also, we do repeat multi-beam sonar at the terminus. And that helps us with two things. Or I guess one, doing the terminus multi-beam allows us to produce imagery that looks like this plot on the left here, where you're seeing a 3D model basically of the terminus. So flow is like into your face from this image. And the bluer colors here are bedrock, or that's the lake, and the green color is the glacier there. And so this is work that Victoria Benson at University of Oregon has been working at, thinking about how you can use the subaqueous terminus morphology to tell you about calving dynamics. So like, is the terminus over-steepened or is it under-steepened, I guess? Is there like a subaqueous toe that could be telling you about rates of subaqueous melt and the vertical distribution of subaqueous melt? But because we have these repeat multi-beam scans, we can basically do sideways DEM differencing to have like a, a volume loss between our two scans. And those produce figures that look like this right one here, where these are showing that we're getting something like 10 centimeters a day of subaqueous melt that's back wearing the glacier compared to surface melt rates of something like 4 centimeters a day. So we're sort of doubling our melt rates because of this glacier being in water relative to being in air. Yeah, and that's those guys at U of O. We've also done CTD casts all through the lake, so you can see those red triangle crosses. There are places where we threw a conductivity temperature depth probe over the side of the zodiac that we were with that show a pretty cold lake. And so these are vertical profiles of temperature and turbidity. And so we're seeing temperatures that are really cold, like less than 2 degrees C throughout the entire lake, and fairly turbid. So you can see this sort of bottom layer in blue here, probably subglacial discharge of very turbid, very cold water. And so we're pairing our hydrographic data with sedimentological data as well. And so this is Jocelyn Reel, as a PhD student at University of Colorado, working with Alina Overeem. And Jocelyn has been using this Van Dorn sampler to try to get suspended sediment samples to think about sedimentation in the lake and how much that might be able to stabilize the glacier over long timescales or not. And she's also using IGM, the instructed glacier model, to try to do the large scale simulation of how much this matters for glacier evolution. And these are just showing an example of the kind of data. So Jocelyn's then able to turn turbidity, which we have from moorings and other observations like water cloudiness, into suspended sediment concentration is the goal, although we see actually a pretty flat relationship here between suspended sediment concentration and turbidity at this site. So we're still working on that. So that's the sediments side. On the glacier side, we have been able to collect a bunch of ice radar. I saw Laurent Mingo on the participants list at some point. So this is thanks to Laurent's radar system that we're running out there. We were able to collect 7 kilometers of radar transects towards the terminus of Gilkey Glacier. This is basically the clean ice side on the south, and then it gets debris covered and pretty hummocky and hard to traverse. We were doing this in summer, so we had blue ice conditions pulling the radar around that made it hard to cover the whole glacier. But you can see we've got these sort of cross-glacier transects as well as a couple of longitudinal transects trying to connect them. And then I just manually picked radar grams to produce ice thickness estimates. And one takeaway we've seen is that any of these large-scale ice thickness estimates seem to be overestimating the ice thickness we see here. Some of that might be a time mismatch. But even when correcting for a difference in acquisition time, it seems like there's pretty significant overestimates of the ice thickness in the Milan and Farinati ice thickness products for Gilkey Glacier and the terminus here. And we've also got on glacier GPS, and we have that in 2 different ways. One is with this continuous on glacier site that actually didn't work super well last field season, as well as stake surveys that we've done with differential GPS. And they show us the glacier is actually flowing pretty sluggishly towards the terminus. We're only seeing like 20 to 25 meters per year of motion, which, if it were really actively, if the terminus were actively perturbing the glacier, I would have thought it was flowing faster. We've tried to put that in context of like remote sensing data. So this is now looking at remotely sensed velocities from image correlation of Landsat and Sentinel data. This is showing a down glacier profile towards the terminus. So the left is up glacier, the right is glacier terminus, and the colors are showing different times, different years. And so you see this blue to yellow trajectory going from high to low, and that's showing the sort of decadal slowing of the glacier. And you also tend to see that the glacier velocity is slowing towards the terminus, indicating that you don't have this like extensional sort of speed up that you often see on marine terminal glaciers. Um, yeah, I might skip through this. It's basically the world's most boring time lapse of the terminus not doing very much, which is I think a sort of our negative finding, just that it doesn't seem like there's a ton going on at the terminus here in terms of iceberg calving at least during our measurement period. But we know from those length change data that it seems like there's pretty substantial time variation in how much calving might be occurring. And so maybe this is just, we chose a sort of quiet time period, as you can see by the stable lengths on that furthest right side of the plot here. Cool. And so just taking you through the trajectory of these slides, we started being more past focused. We then talked about what we're doing now, and I'll now try to look a little bit forward. And so to do that, we'll take the modern lake extent and basically look up glacier, which we're able to do by combining a bunch of different digital elevation data sets and a bias adjusted ice thickness estimate that we basically forced the Milan ice thickness data to match our ice radar measurements, where we can now be producing maps like this of bed elevation below the glacier and think about what's going to happen as the glacier continues to retreat. Is it going to be a lake, or is it going to switch to land terminating? And we can see plots like this that are showing the forecast water depth in the future, assuming that the lake surface elevation stays the same as it is at present. And I guess key takeaways from this are that Gilkey Glacier isn't expected to retreat out of this terminal overdeepening for 8 more kilometers, and that the deepest water depth that we're going to see is actually still to come. So that 200 meters of water that we see in the lake right now will likely be surpassed by water depth as the glacier continues to retreat through this next overdeepening. I might skip through this to try to just save some time, but we're basically thinking about is the thermal structure of the glacier going to stay the same? Is the thermal structure of the lake going to stay the same as the lake grows bigger, or could it turn more like a Patagonian glacier that's much warmer and start to have substantially more mass loss? Yeah, and so I guess the broad conclusions that I want to end on are that there's these covariance between glacier terminus types, such that you really need process studies, or at least better correlational studies, to say what is the influence of frontal ablation. We've started this multidisciplinary project to try to do just that. We see that it seems like calving and subaqueous melt vary substantially in time in these cold, deep lakes like Gilkey Glacier ends in. And yeah, this project is I guess we have one field season done. We're going to be going out again this next field season to go back to Gilkey Glacier as well as Field Glacier. And then we have one more year as well of sort of collecting odds and ends. And maybe I'll actually leave it with this slide, as I have questions with this in the spirit of being a collaborative workshop. I think there's lots of ways that we would love to have the data that we're collecting be useful for others. And vice versa. I mean, what makes, I think, the Juneau ice field so great to work on is the tons of different people there working on different angles of the ice field and producing different data sets that will allow us to better constrain our problem. And so I would love to talk with folks about anything that we can help you with, or vice versa. If you have data sets you think could help us with, we would love to incorporate them. So thank you all.
Any questions from the room? Philip?
Thanks for a great talk. I was wondering about the ISSN model, where there was like a big jump backwards. Like you got different timings for retreat based on calving, but like in each of them, it seemed like there was this one big jump in the terminus position. Like, what do you think is driving that in that model?
Yeah. So sorry. I think I heard you say, but ISSM, like, I'll just go back to this slide. Yeah, I mean, I think it's a good question. It's actually something I'm trying to kind of figure out, like how to best use ISSM to try to constrain this question, because I think it's the kind of thing where we're not really trying to get like the exact uh timing of this big stepped retreat event, but more like can you get the general kind of dynamics? Like, do we see fluctuations between sort of more gradual retreat, driven by, I think, largely like grounded terminus conditions, and then more rapid retreat when it switches to a floating tongue? And it seems like ISSM is able to do that well. Um, and yeah, I guess I don't exactly know how much uh, like emphasis or stock to place on like the exact values. You probably can't even read these exact values, thankfully, but it's like 10 to 20 kilopascals is what we had as the stress cat, the criterion for calving in this von Mises calving rule. And yeah, I guess I don't think I totally answered your question, but like it's something I'm still trying to think of how to best use this model. And if you have ideas, I would love to talk more over email or something else. I wish I could be there with you all. It's always better to be there in person, but I couldn't swing it this time.
Billy, great talk. Thanks for going through all the data. I'm curious, in your GPS observations, did you see any like, you know, daily, seasonal, or weekly variations in velocities or seasonal speed up or anything like that in your data sets?
Yeah, we didn't see a ton. So like this is the setup we have here, which is there are these UNAVCO basically like free giveaway GPSs. So it's a TopCon antenna in the box is a NetRS receiver. And I don't know if it was the combining of these different kind of components or something, but we really didn't get great data from these things. It's moving pretty slowly, the glacier, but it seems way noisier than I would have expected. And so I like don't have the GPS data in this presentation. And that's partly because they just are kind of too noisy to show diurnals, or even kind of like this was a faster period versus this was a slower period. All they really seem very good for is getting like an average over this time span. One thing we do have are these data here, which is basically the like unwrapped version of what I just showed you. And so this is, again, this is from its live data. So this is satellite image correlation derived velocity time series near the terminus of Gilkey Glacier. And what I was trying to look for is basically, do we see like accelerations associated with rapid terminus retreat where you have some kind of like marine ice sheet instability kind of thing going on? And to me, the answer seems like nothing clear, at least. Like we have a lot of wiggles in the velocity time series that I think are partly related to Gilkey Glacier being east-west flowing. And that means that in feature tracking, you kind of get messed up by different shadow casting as you go between seasons, because the sun is at varying elevations behind the ridge. And so I think that adds potentially spurious seasonal signals, but there's nothing that like really jumps out. I mean, there's some periods where we see faster flow, maybe slightly preceding a rapid retreat event. So like maybe that's a signal, but it also feels like you're running a risk of like overinterpreting squiggles too.
Gotcha. And I have a couple follow-up questions. That that ice thickness that you show. I mean the you know have you all talked about the potential for significant rapid retreat when it reaches that potential deep over thickening, kind of like the reverse bed slope issue with
Yeah,
ice?
totally. Yeah, I'm interested, and so I guess maybe this is like the better
Yeah, that one. Yeah,
slide to show for
exactly.
that. Yeah, I'm really interested to see. I mean, it seems like basically we're at a period right now where in this little flow constriction here, it's narrower here, and we could see from the multi-beam data that there is a moraine close to the terminus, and so we're in this like quiescent sort of period. It seems like where the glacier, either that flow constriction or the shoaling associated with that moraine, has resulted in slower retreat in the past like 3, 4, 5 years. But from like this kind of data, you can sort of see that these periods of quiescence where you have either stability or even subtle advance, they always seem to precede these rapid retreat events. And so I do wonder, it might not be in our project's lifetime, but is this just sort of like a quiet period before entering another phase of rapid retreat? I would guess the answer is yes, but that's more like speculation than anything that our data can actually say yet. But I'd
Seems
like
like
to be able to say
really,
that more quantitatively.
seems like a key piece of data would be constraining the ELA change too as you move forward to answer your chicken or egg problem.
Yeah, totally. And so what we've been doing so far, and this is where talking about the Juneau ice field as a whole is so cool, is we've been using Ryan Ing, I think I'm saying his last name right, ING. But that group, who I can't remember, it's in the UK that they were working. They have a energy balance model, or like a really good melt model across the whole ice field, and we have been using their data basically just as a forcing for our ISSM model, as well as the IGM, the instructed glacier model. And so we've sort of been, I guess, able to offload the work to other researchers who have looked at it in more detail, but it probably will be something good for us to zoom in on a little more too, is thinking about ELA rise.
I guess my last question I had is I mean, it's in relation to the reason I asked about the speed up is in relation to some of the work that we're doing. We are installing multiple terrestrial radar interferometers on the ice field this year, one in a radome at Camp 18 looking at the Gilkey. And our goal is kind of looking at lateral margin instability. But with that comes a thought process about if you have variation in speed, variation in water pressure, things like that, does that influence your lateral margin stability? And one of the things we thought about is trying to sync up a TRI observations from the trench with another TRI installed down by you guys looking at the glacier terminus, but also the marginal activity as well. So I didn't know if that was something you all might be interested in.
Yeah, definitely. That would be super cool. I mean, you can see that the terminus here is so cracked up that, I mean, we're getting as close to the terminus as seemed feasible for moving through, and also in terms of not losing instrumentation on the ice. But yeah, something like a TRI would be awesome for getting spatially distributed information, and information that goes like right up to the terminus would be really helpful for us, especially with the drone restrictions that NSF has now. A TRI would be really helpful, as long as that hasn't been banned as well.
All right, let's talk over break over the next week or so.
Yeah,
Thanks,
thanks,
Billy.
guys.
Billy?